are multiple types of distances that you can use to measure the similarity and differences. Each one of them works best with their own, each one of them invented based on a problem, based on a use case, based on a data set. So sometimes in certain situations, some of them can be interchangeably used, but then sometimes you need more precision and you cannot do that. Euclidean, as we talked about, is the most straightforward distance that you can measure between 2 points. It's just the shortest distance that connects point A to point B. And then it's the same as Pythagorean theorem that we know about it. It just measures the line that is connecting point A and point B to each other. And then we have Manhattan. It's not the shortest distance, but it is just, for example, if you have an X and a Y and it connects these two lines together, you will add the lengths of X and add the lengths of Y together, and that is going to be the Manhattan distance. From here, we can understand that the Euclidean distance should be shorter than Manhattan distance. And then you would think, well, why do we want to do that? So for example, when you want to get a direction from one point to another point, you don't want to know what is the shortest line that can connect these 2 points together. So that is going to be useless. For example, these 2 points might be very close together, like the shortest line that is going to add these 2 points together is going to be very short, and you would say, okay, well, from here to there, it's just half a kilometer. But you actually don't have any straight street or any line that you can directly go to that point. You actually have to go all the way across from all the buildings and then go to the other points. If your data set is a data set that a certain weight is very important, like for example, what are the chances that someone graduate from school? For example, you have, I don't know, the height of the student, you have the height of the student, you have the hours that the person studied, you have the age of the student, you have so many of these variables, okay? Some of these variables are more important, some of these features are more important than other features, okay? So for example, the height of the student is not that much relevant to the person graduating than the time that they spend studying. Cosine similarity is not something that you want to go for, because cosine similarity is one of those distances that disregard of the weight of each one of these data points, and it goes with the direction. Cosine similarity is used for similarity between documents, like plagiarism detection and things like that. If I want to give you a very simple example, the person says this is very good, and then the other person wants to say, oh, I said something different. So what they do is they're going to say this is very, 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 very good. And then if you're looking at the distance that's going to measure, that's going to give value to each one of these data points, these two are not going to be similar. But when you're using something like cosine similarity, it does make the weight more, so the vector is going to be longer, but it is pointing at the same direction. If it is very, it is very. If it is good, it is good. And then it's going to measure, and then the more similar that they are, the closer the number is going to be to 1, because both of the vectors are going to point at one direction. Sometimes it is not feasible to only use Euclidean distance or only use Manhattan distance to reach your destination, because the goal is here to measure the distance between the start points and the destination. So all the way to the destination, you want to measure this distance. An example for that would be, for example, when you want to travel from Toronto to Vancouver. You're not going to directly go from this point to that point. You can't teleport. You can't get to the airplane from your home. What you have to do is you have to actually drive to the airport. And it is true that we are living in three-dimensional world, but because of gravity, you cannot travel in the z dimension. You're mainly traveling in x and y dimension. And even then, you cannot go through the obstacles that are between you till you reach the airport, because there are houses, there are streets, you're supposed to go a certain path. So you cannot do even Euclidean distance in two-dimensional world. So you have to use the Manhattan. So you use the Manhattan, you reach to airport, and then from there you're using, we're going to just simplify this, you're using the Euclidean distance between Toronto to Vancouver, because you're getting into the airplane and you're traveling to Vancouver. Euclidean itself wasn't able to take you to the destination, and also Manhattan itself wasn't able to take you to the destination. It was a mixture of these two that took you to your destination. When we're doing something like that, our calculation is going to be a little bit different, and it is called Minkowski distance. The whole point of the distances that are grouped under Minkowski is that they're going to measure the distance until the destination, from the start point to the destination. Chebyshev concept is a little bit different. First, let me talk about the use cases. Imagine you're playing chess. You can't do all of the moves that you want to make in one go. You have to make a move and then wait for the other person to make a move. For example, imagine if your king is at e4 and you want it to be at e6. You cannot do it in one move because king, as you know, only can move one square at a time. The whole point is that in Chebyshev, you don't necessarily reach your destination. You're just making the biggest step that you are capable of making in your turn in order to reach your destination. So Jaccard is very similar to cosine in some aspect. In some aspect, it's completely different. So both Jaccard and cosine similarity tries to figure out how two sets of data are similar to each other. And we already talked about cosine before, so we know that cosine is actually a vector. It doesn't care about the weight. We are looking at the direction. We were talking about the direction. It is very important that our data set be dense, okay? When you have so many zeros for each one of these data points, for the features that are representing each one of these data points, that basically means that your data set is in high dimension. And as we talked before, the higher in dimension that you go, the more sparse your points are going to be. So the chances of them pointing at one direction will become lower and lower. For example, let's talk about the students in a class. If you are trying to only separate the students in the class as in male and female, and the females are all going to point at one direction, males are all going to point at one direction. And then you start adding more features to it. You start adding the months that they born, you start adding the amount of time they study per day, you start adding their age and other things like this. When you keep adding these things to your data set, they're not going to be similar anymore. So your vectors start like separating. Okay, so that's what happened with high dimensionality. If you are in high dimension but your data set is dense, you're still going to be fine. If you have so many zeros, you have so many dimensions around you that are zero, okay, but they are still there. And then when one of them is 1, it's going to drastically change the direction between two vectors a lot, because you have so many dimensions for these vectors to spread out. The way that Jaccard calculates is just counts the number of the ones that are similar to the total number. And Jaccard is very good in sparse data that has lots of zeros in it. But when you're having too much data, when your data set is very dense, then it won't be able to tell that much differences, because you might, when you have like 300, 400 word documents, and each one of these words are going to be a feature, chances of these words being similar in two documents is high, but the orientation of these words might be in a way that these two documents are going to be completely different. Each one of these similarities that we talked about, cosine, Jaccard, and Gower, each one of them have some strengths and they have some weaknesses. Cosine does not go through every feature. It takes all of the feature as a whole and says this data point in all of the dimension that it exists, it's pointing this direction. The other data point is pointing this direction. The other data point is pointing this direction. And then if these two data points, if two of these data points are pointing at the same direction in cosine, and they are going to be similar. Okay, if they are at 90 degrees, that means they are dissimilar, because the cosine for 90 degree is 0, so there's no similarity. If they are at the opposite direction, then they are going to be -1. So pointing at the same direction, and then all of this in between is going to be. But for Jaccard and for Gower, they are both going through the features of each data point and they say which features are similar to other features. We have a data set, and then we are considering 2 points from this data set. So each one of these data points have 100 features still, only 20 of them are 1. And then, okay, Jaccard is very good at binary as well, binary data. Jaccard is not going to consider 100 features, okay? The denominator for Jaccard is going to be 20, because these two data points together, they have 20 features, okay? And between these 20 features, 5 of them are similar. And at the top, you're gonna have the ones that are similar between these two. So as you can see, Jaccard is doing well with binaries because it says if you have a feature or if you don't have a feature. Gower is still going through each single one of those features, okay, but what it does is that even if you have different type of features, if you have, for example, some of them are categorical, some of them are ordinal, but then it will transform the data. It will transform the data in order to be able to use it. So it makes all of them of the same kind. So this way, it's going to normalize the whole data set. And Gower, because it has high capability of comparing multiple types of data set with each other, it's not ideal for large data set because it's going to be expensive, as in it will use a lot of memory and a lot of CPU power because it's going through every single point that you have in your data set and it's going to compare them with each other, and it has to transform the whole features, like different type of features that you have. So depending on your use case and what you want to do, you have to choose between these.